Alright, now that we have learned a little bit about electronic configuration, I want to do some problems for you guys. The picture on the right shows, it's figure 7.24 in your book, and it shows the order in which the atomic subshells are filled in a many electron atom. So you could use this figure to help you. Just kind of memorize what it looks like, and you can write it down on your test when you get there. But this is how, in general, the subshells are filled. So using this figure, let's see if we can come up with the electron configuration of the following elements. The first one will be vanadium. Vanadium is element number 23. It's in the transition metal block. So I'm going to do it the long way, and then we'll do it the shorthand way. So to get to vanadium, I have to go through all the rows first. So 1s2, 2s2, 2p6, 3s2, 3p6, and then I'm in 4s2, and then I have to go to the transition metal, which you have to minus a row. So it would be 4s2, then 3d123. Shorthand way would be bracket around argon, and then all you do is have the valence electrons, which is 4s2 and 3d3. Alright, now I want to try nickel. Nickel is actually number 28, element number 28. It's also in the 3d row of the transition metal. So we're going to just do it the shorthand way. I'm going to do argon in brackets, and then I'm going to do 4s2, and then I have to count the d's that it's in. So nickel is 1, 2, 3, 4, 5, 6, 7, 8. So then my shorthand would say argon in brackets, 4s2, 3d8. Now I want to introduce to you some irregularities. The transition metals, everything fills up pretty much like I said in the figure, but there are some irregularities, and they mostly come when you deal with the transition metals and the lanthanide and actinides, which is the F, the people on the bottom, the elements on the bottom. Alright, and the problem is the transition metals have incompletely filled d subshells, so they tend to do funky things sometimes. I've shown you two transition metals that fill up pretty much normally, but then you get to chromium. Okay, and chromium is element number 24. And you would expect, if we followed Aufbau principle, the building up principle, you would expect the electron configuration to be argon in brackets and then 4s2, 3d4. But it's not. The ground state electron configuration of chromium is argon in brackets, 4s1, 3d5. And the reason is because it's obviously less energy to have a half-filled 3D subshell than it would be to have only 4 electrons in the 3D subshell. So there's a slightly greater stability associated with the half-filled the D subshells. And the same concept goes for the F, the elements in the bottom. So there's some sort of stability that happens within the atom when you have half-filled F subshells and half-filled D subshells. So chromium would be one of these irregularities that you would see. And then if you go to the next one, which I have is copper. Copper is element number 29. And if you notice, it's basically number 9 in the D subshell, right? So it'd be scandium is number 1, then titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and then you have copper. Alright, but copper would be number 9 in that D subshell. So what do you think the electronic configuration would be? Think about what I just said. There's greater stability with a half-filled D subshell, so don't you think there would be a greater stability for a full D subshell? Yes, that is the case. So another irregularity that you see is these guys that sit in positions 9, right? So what happens is that one of the S electrons, the S orbital electrons, will promote itself to fill that D subshell. So instead of copper being argon in brackets 4s2 3d9, Instead, it takes the form of argon in brackets 4s1 3d10, because it again feels greater stability with that d subshell completely filled than if you just have 9 electrons with one unpaired electron. That just seems like it would take more energy. And then I threw in something like element number 41, which is called niobium. Niobium is an exception to every rule. If you look on page 311, which has all of the electronic ground state electronic configurations for all of the elements that we have on our periodic table, you look for number 41 and you see that the electronic configuration is krypton 5s1 4d4. That doesn't make any sense whatsoever with any of the rules that we've talked about so far. So that clearly is an exception to the rules. Okay, so you see Aufbau principle works mostly, and you can use this little figure to help you remember how to fill up the orbitals. Of course, we're following the arrows, so you would fill up 1s first, then you would fill up 2s, then you would fill up 2p, then you would fill up 3s, and then you would fill up 3p, 4s, 3d, 4p, 5s. So that's how you read this figure, but there are exceptions to that rule. One exception that I've showed you right there is element number 41, niobium. It's 5s1 4d4. You would expect it to either be 5s2 4d3 or maybe 5s0, like both electrons get promoted to the d subshell, making it 4d5, but it doesn't. It's completely odd, 5s1 4d4, and maybe it has to do with the fact that there's less repulsion within this s subshell. Since the s subshell is smaller, there might be less electron repulsion, whereas if you have 5d3, there's a lot of, those are all spin up electrons, so maybe that creates a lot bigger repulsion in the d subshell than it would in an s subshell, which is smaller. So, there's all kinds of exceptions and stuff, but there's only a couple of them, and I wouldn't worry too much about them, but I did want to show you them. Alright, so I think that you guys should keep practicing these, and the best thing to do is look on page 311. Look at those elements, see and go through them and see how they make their electronic configurations. Try to make sense of those. And we'll do some more in class, and we'll take care of also cations and irregular atoms like this. This is problem 791 in the back of your chapter, and it reads, the electron configuration for a neutral atom is 1s2, 2s2, 2p6, 3s2. Write a complete set of quantum numbers for each of the electrons. Name the element. We did something like this in class. I just wanted to go through it. So we have to figure out what the addresses are for each of the electrons in this atom. If you count up all the subscripts, you'll see that there's 12 electrons. That's why I've put 12 rows. So we have to find the N, the L, and the M sub L, and the M sub S for each of them. I'm going to go through this pretty quickly, so just pay attention. So the first electron would be the 1s1, right? So that would have an N of 1, a L of 0, because S is equal to 0, an M sub L of 0, and a spin number of plus 1/2. The second electron is going to have, it's the same 1s subshell, but it's the second electron, so it would be exactly the same, 1, 0, 0, and then minus 1/2. Now you move on to the third electron, which you start in the 2s, right? So you're basically giving the address for the 2s1. But the N is going to be 2. The L is going to be also 0 because it's still an S. The M sub L has to be 0, and then the M sub S is positive 1/2. The fourth electron is going to be exactly the same, but with minus 1/2. So 2, 0, 0, minus 1/2. Now we go to the fifth electron. That's the first one in the P's, right? So we're in second row, 2p6, but we're going to do the first one of those, first electron of those 6. So it's going to be N is equal to 2. Since now we're in the P's, the L must equal to 1. And there's 3 different orientations for a p. So I'm going to start with the negative one. So it's going to be 2, 1, negative 1, and then spin up, plus 1/2. And then I'm going to go to the next orbital, or the next electron, excuse me, the 6th electron, which would be n equals 2, L is equal to 1 still, because it's a p, but I'm going to move on to the next orbital, which is 0, and then my spin number will be plus 1/2. Then I move on to the 7th electron. It's 2 for n, 1 for the L, because we're still in the p's, and then I'm going to move on to the other orbital, which is plus 1, and then my spin of plus 1/2. My 8th electron now goes back to the first orbital. Okay, so your principal quantum number 2, L is equal to 1 because we're still in the p's, but I'm back at the first orbital, the negative 1, but except this one is going to have a minus 1/2 for the spin. Completely different address. Alright, so the 9th electron is 2, 1, 0, we're going back to the middle orbital, minus 1/2. And then the 10th electron, which is the last one of the p's, is going to be n equals 2, L is equal to 1, m sub L is plus 1, we're in the last orbital, but the spin number is minus 1/2. Now we're in the last 2 electrons, but we're back at the s. Row number 3, back at the s. So n would be equal to 3. If you have an s, it equals 0 for the L. So that's going to be 3, 0, and then m sub L has to be 0, and then you have a minus 1/2. Or, excuse me, a plus 1/2. And then you do the second electron in that third row in the s orbital, which would be 3, 0, 0, minus 1/2. Pretty simple. If you can do this, you're understanding what's going on. I want to do one more problem. This is the last problem I'm going to do. It's problem 792 in the back of your chapter. It reads, which of the following species has the most unpaired electrons? S plus, S, or S minus. So it's sulfur. So either a cation of sulfur, neutral, or an anion of sulfur. So the first thing I'm going to do is I'm going to write down what sulfur is, neutral. So I'm going to do it the shorthand way. Sulfur is neon in brackets, and then 3s2, 3p4. So that I'm going to put that down. Since we're in the p's, that means I have 3 different orbitals. So I'm going to put 3 different lines, and I'm going to fill up 4 electrons. So spin up, spin up, spin up, and then go back to the first orbital, spin down. So this one has 2 unpaired electrons. I'm going to now do S plus, the cation. So what that means is that there's 1 less electron in that p orbital. Instead of being 3s2, 3p4, it's actually 3s2, 3p3. So all I'm going to have is in those 3 orbitals, I'm going to have 1 electron spin up in each of the orbitals. So that has 3 unpaired electrons. Well, this one's winning so far. How about S minus? S minus is an anion of sulfur, so that means that basically you're going to add 1 more electron to those orbitals. So instead of being neon bracket 3s2, 3p4, it's going to be 3s2, 3p5. So it's going to be spin up, spin up, spin up, and then spin down, spin down. So this one, that's total 5 electrons, and this one only has 1 unpaired electron. So the species that has the most unpaired electrons would be the cation of sulfur, because it has 3 unpaired electrons. Alright guys, I hope this is becoming easier for you. We'll do some more of these in class. See you later.